In this video, we'll see how to sort a linked list using merge sort. To know about the merge sort algorithm, you can go to the sorting section and watch the video on recursive merge sort. To sort an array of size n, we need an extra array of size n. But in linked list, we don't need any extra memory because we can perform the merging process by rearranging links. Now this is the public method which will sort our linked list using merge sort. Inside this method, we are calling this private recursive method. So now let's see how this private recursive method works. This list start is reference to first node of the list that has to be sorted. This is the terminating condition of recursion. If the list is empty or has only one element, then we'll return list start from this method. Otherwise, if the list has more than one element, then we'll divide our list into two lists of almost equal size. Start 1 refers to first node of the first list and start 2 refers to first node of the second list. These two lists are recursively sorted using this method. Now after sorting these lists, they are merged using this method merge 2. We get a reference to the first node of the merged list and this reference is returned from this method. This method merge 2 we have already seen in the previous lecture. This is the method merge 2. It merges two sorted lists by rearranging links. These references P1 and P2 refer to first nodes of the two lists that are to be merged. We have already discussed how this method works. So now let's see how we can divide our list into two lists of almost equal size. Start 1 is reference to first node of the first list. Now start 1 is equal to list start. So start of first list is actually the start of original list that has to be divided. And start 2 is reference to first node of the second list. And this start 2 is obtained by this method divide list. So now let's see this method divide list. We have taken two references P and Q. P initially refers to first node of the list that has to be divided and this reference Q refers to the third node of that list. Now inside this loop we are moving P one node at a time and Q two nodes at a time. And this loop will terminate when either Q becomes null or Q link becomes null. Q will become null if the list has even number of nodes and Q link will become null if the list has odd number of nodes. Now after this loop terminates, we'll assign P link to start 2 and we'll put null in P link. And then we'll return start 2 which is reference to the first node of the second list. Now let's understand this with the help of an example. Suppose this is a list that has to be divided. This is the code that will divide this list. Initially, P refers to the first node of this list and Q refers to third node of the list. Now we'll move P one node at a time and Q two nodes at a time. So we move P, we move Q, we move P, we move Q two nodes, we move P, we move Q. Now Q becomes null. So this loop terminates. Now we make start 2 equal to P link. So the reference start 2 refers to this node and we make P link equal to null. So this becomes null. So now we can see that our list has been divided into two lists and this start 2 refers to the first node of the second list. Now let's go back to our program. So we have seen how this divide list method works. In our method main, we have called this merge sort method in case 15. Here we've called this method merge sort. Now let's run this program. This is our initial list. And this is the sorted list. In this video, we'll see how we can find and remove a cycle in a linked list. In this list, these 5 nodes form a cycle. This list is not null terminated and so it has no end. Now one solution to find cycle in a linked list is to keep a visited flag in each node and start traversing from the beginning of the list. And whenever a node is visited, its visited flag is set to true. So if the list has a cycle, we'll definitely come back to a node whose visited flag is true. Now in this solution, we have to make changes in the node. Another solution in which we don't have to change the node is to use the hare and tortoise algorithm. It is also known as Floyd's cycle detection algorithm. In this algorithm, we take 2 references, one slow reference and one fast reference. And initially we make both these references refer to the first node of the list. After that, we move both references. The slow reference moves one node at a time and the fast reference moves 2 nodes at a time. If the list is not null terminated, that is, it has a cycle, or if the whole list is circular, then definitely at some point both the references will meet at a node. And if the list does not have a cycle, that is, it is null terminated, they will never meet. So now let's start and see how we can find cycle in this list using this hare and tortoise algorithm. We'll take 2 references, one slow reference and one fast reference. This slow reference denotes a tortoise and it will move one node at a time. And this fast reference denotes a hare and it will move 2 nodes at a time. So now let's move them. This slow reference moved one node and this fast reference moved 2 nodes. Again we move them. Again we move them. Now when we'll move this slow reference, it will come here. And when we move this fast reference, it will come at this node. Now when we move this slow reference, it will come here. And when we move this fast reference, it will also come here. So now both these slow and fast references meet at a node. This means that the list has a cycle. Now let's see the code for this. This method has cycle returns true if the list has a cycle. Otherwise it returns false. Inside this method, we have called this private method find cycle that actually detects the cycle in the list using hare and tortoise algorithm. Now this method find cycle will return null if the list does not have a cycle. Otherwise, it will return reference to the node where slow and fast references will meet. Now if start is null or start link is null, we'll return null from this method. We take 2 references, slow reference and fast reference, and initialize both these references to start. So initially, both these references refer to the first node of the list. Now inside this loop, we move slow reference one node at a time and we move this fast reference 2 nodes at a time. If slow reference and fast reference become equal, that is, they meet at a node, then we will return reference to the node where they meet. This will happen if there is a cycle in the list. If the list is null terminated, that is, it has no cycle, then this loop condition will become false and the control will come here and null will be returned from this method. If the list is null terminated and has even number of nodes, then this condition will become false and the loop will be terminated. And if the list is null terminated and has odd number of nodes, then this condition will become false and the loop will be terminated. So if the list is null terminated, then null will be returned from this method. Now let's see the method remove cycle. To remove cycle from the list, we need to find out the length of the list, that is the total number of nodes in the list. Once we find out the length of the list, we can easily make it null terminated by placing null in the link of the last node. Now to find out the length of the list, first we'll find out the length of the cycle, that is number of nodes that are there in the cycle. After that, we'll find out the length of the remaining list, that is the number of nodes that are not included in the cycle. After that, we can find out the length of the whole list by adding these two. So now let's see how we can do this. This is the node where the slow and fast references met in hare and tortoise algorithm. Now for finding length of the cycle, we'll take 2 references referring to this node We'll fix one reference and we'll move the other reference one node at a time. And we'll stop when both these references meet again. So we'll fix this reference P and we'll move this reference Q one node at a time. And the number of times this reference Q moves will give us the number of nodes in the cycle. Because this Q will move one full cycle before meeting this P again. So let's move this reference Q. So this Q moved 5 times before meeting this P again. So length of the cycle is 5. That is, the number of nodes in the cycle are 5. Now we'll see how we can find out the length of remaining list. For this, we'll let the reference Q be here only and we'll take this reference P to the first node of the list. Now we'll move both these references one node at a time till they meet. So the number of times they will move before meeting will give us the length of remaining list. So now let's move them. So these references moved 3 times before meeting. So the length of remaining list is 3. That is, the number of nodes that are not in the cycle is 3. We can find the length of the whole list by adding these two. So the length of whole list is 8. Now we can easily remove the cycle from the list by taking a reference to first node of the list and moving it 7 times and then placing null in its link. So now let's move this reference 7 times. 1, 2, 3, 4, 5, 6 and 7. Now we place null in its link. So now we can see that the cycle has been removed from the list and the list has become null terminated. Now let's see this method remove cycle. Inside this method, first we have called this method find cycle. That will return the reference to the node where slow and fast references meet. Now we have taken two references P and Q and we have made both of them refer to the node where slow and fast references meet. Now here we are finding the length of the cycle. We are moving this reference Q one node at a time till it meets P again. We have taken a do-while loop because initially P and Q are same and so a while loop will not work here. Now the number of times this reference Q moves before meeting P will give us the length of the cycle. Now after finding the length of the cycle, we are finding the length of the remaining list. For that we have not changed Q and we have made this reference P refer to the first node of the list. We move both P and Q one node at a time till they meet. So the number of times they move gives us the length of the remaining list. Now we find the length of the whole list by adding these two. And at the last we are removing the cycle from the list. So we have taken a reference referring to first node of the list. We move this reference length list minus 1 times and we place null in its link. So this is how we can remove cycle from the list. Now for finding and removing a cycle from the list, we need a list that contains a cycle. So we have made this method insert cycle that will insert a cycle at a node that contains value x. We have taken this reference P and made it refer to the first node of the list. This loop executes till P is not equal to null. This reference previous is always one node behind reference P. When P info becomes equal to x, we will save value of P in Px. And after this loop terminates, we will assign value of Px to link of previous. Now let's see how we can do this. Suppose we have to insert a cycle in this list at the node that contains 40. So we have to insert this cycle in the list. We'll take a reference referring to first node of the list. We'll take a reference previous that will always be behind this reference P. We'll move both these references. Now P info is equal to 40. So we'll save the value of P in Px. Again we'll move these references P and previous till P becomes null. Now P has become null. So we'll make the link part of previous refer to this node. So this is how we have inserted the cycle in the list. Now let's go back to our program and run it. This is our initial list. Now we'll insert a cycle at the node that contains value 4. Now we'll detect the cycle. List has a cycle. Now we'll remove this cycle. So the node at which the cycle was detected is node 6. Length of cycle is 5. Number of nodes not included in the cycle are 3. And the length of the whole list is 8. Now the cycle has been removed, so we can display our list. In this video, we'll learn about doubly linked list. In a doubly linked list, each node has 3 parts, one info part and 2 link parts. One link part refers to the next node and one link part refers to the previous node. For the first node of the list, this previous link is null, and for the last node, this next link is null. Now let's see the advantages and disadvantages of a doubly linked list. The first advantage is that it can be traversed in both forward and backward directions. While in single linked list, we could go only in forward direction. Here, if we want to go in forward direction, we can follow these next links, and if we want to go in backward direction, we can follow these previous links. Second advantage is that implementation of some operations is easier. Insertion and deletion can be done with a single reference. For example, for deleting a node in a single linked list, we need a reference to the predecessor node. Now, in case of doubly linked list, we just need a reference to the node that is being deleted, because the information of previous node is present in the node itself. So if you have to delete a node from the list and you're given only a reference to that node, then doubly linked list is more efficient. As in single linked list, we'll have to traverse and find the reference to predecessor node. Similarly, the case of insertion before a node is easier. As in doubly linked list, we'll not need a reference to the predecessor node. Now let's come to disadvantages. The first disadvantage is that extra space is required for storing the previous link in each node. And the other disadvantage is that while performing insertion and deletion operations, we have to do some extra steps for maintaining the previous link. Now let's see how we can implement a doubly linked list in a program. This is the class node that represents a node of a double linked list. We have taken 2 references of type node. This reference refers to the previous node and this reference next refers to the next node. This info we have taken of type int. And this is the one argument constructor. Now this is the double linked list class. We have taken this reference start that will always refer to the first node of the list. And in this constructor, we are initializing the start to null. This method display list displays the list. So if the list is empty, we'll print this message. Otherwise, we'll traverse the whole list from beginning to end and print the info part. After this, we have different methods for insertion, deletion, and reversal. So in the next few lectures, we'll see how to write all these methods. Now this is the method main in which we'll test our double linked list class. So here we are creating a new object. After that, we are creating the list using this method create list. And in this while loop, we are performing different operations on the object. We are displaying the list, inserting, deleting, and reversing the list. In this video, we'll see how to insert a new node in a doubly linked list. These are the different cases that we'll see. So first, let's see how we can insert a new node in the beginning of the list. We allocate a new node. Now the next part of this node should refer to this node. So we write temp next is equal to start. Next, the previous part of this node should refer to this node. So we write start previous is equal to temp. Next, we'll update start and make it refer to this new node. So we write start equal to temp. We'll let this previous link remain null only, as this is the first node now. So this is how we can insert a new node in the beginning of the list. Now let's see how we can insert a new node in an empty list. For an empty list, start is null. We allocate a new node and we make start refer to this new node. So we write start equal to temp. Now this is the first node of the list, so its previous link should be null. and this is also the last node of the list, so its next link should be null. So we will not change the two links and we'll let them remain null only. Now we'll see how we can insert a new node at the end of the list. For this, we need a reference to the last node of the list. We allocate a new node. Now the next part of this node should refer to this new node. So we write p next equal to temp. Now the previous part of this new node should refer to this node. So we write temp previous is equal to p. Now we'll not change the next part of this node because it is the last node now and its next part should be null. So this is how we can insert a new node at the end of the list. Now we'll see how we can insert a new node after a node. Suppose we are given this reference p and we have to insert a new node after this node that is referred by p. So we allocate a new node. Now the previous part of this node should refer to this node. So we write temp previous is equal to p. The next part of this node should refer to this node. So we write temp next is equal to p next. Now the previous part of this node should refer to this node. So we write p next previous is equal to temp. Now the next part of this node should refer to this node. So we write p next is equal to temp. The order of these two statements is important. First we should write this statement and then only we should change this p next. So this is how we can insert a new node after a node. Now we'll see how we can insert a new node before a node. Suppose we are given reference to this node and we have to insert a new node before this node that is referred to by p. So we allocate a new node. Now the previous part of this node should refer to this node. So we write temp previous is equal to p previous. Next part of this new node should refer to this node. So we write temp next is equal to p. Now the next part of this node should refer to this node. So we write p previous next is equal to temp, and the previous part of this node should refer to this node. So we write p previous is equal to temp. So this is how we can insert a new node before a node. Now let's see the code for all the cases of insertion. This method inserts a new node in the beginning of the list. This method inserts a new node in an empty list. And this method inserts a new node at the end of the list. Here we are finding reference to the last node of the list and then we are inserting the new node. This method create list we have made with the help of these two methods, insert in empty list and insert at end. For inserting the first node, we are calling this method insert in empty list, and for inserting rest of the nodes, we are calling this method insert at end. Now this method insert after will insert a new node after the node that contains this key value x. Here first we are finding reference to the node that contains x. So after this loop terminates, if p is null, it means that x is not present in the list. Otherwise, we'll insert the new node after the node referred to by reference p. Now this statement should not be written if p refers to the last node, because in that case p next will be null and accessing p next previous will give us error. So this statement should be written only when p does not refer to the last node. Now this method insert before will insert a new node before the node that contains this key value x. If the list is empty, we'll just return. If x is present in the first node, it means that we have to insert the new node in the beginning of the list. So we'll insert the new node in the beginning of the list and return. Otherwise, we'll find reference to the node that contains x. So after this loop terminates, if p is null, it means that x is not present in the list. Otherwise, we'll insert the new node before the node referred to by reference p. Now in main, we have called these methods in cases 3, 4, 5 and 6. Now let's run this program. First we create a new list. So this is our initial list. Now we'll insert a new node in the beginning of the list. So now this is our list. This node is inserted in the beginning of the list. Now we'll insert a new node at the end of the list. Now this is our list. Now we'll insert a node after a specified node. So we'll insert this node after node 3. Now this is our list. This node has been inserted after this node 3. Now we'll insert a new node before a specified node. We'll insert this node before node 4. So now this is our list. This new node has been inserted before this node 4. In this video, we'll see how we can delete a node from a doubly linked list. These are the different cases that we'll see. So first, let's see how we can delete the first node of the list. Now we have to delete this node. So after deletion of this node will become the first node of the list. So start should refer to this node. So we write start equal to start next. Now this node has become the first node of the list. So its previous part should be null. So we write start previous is equal to null. And now this node has been removed from this list. Now let's see how we can delete the only node of the list. For deleting the only node of the list, we just have to write start equal to null. And this node is removed from the list. Now this was the case of deletion of the first node of the list. We can see that these two cases have to be handled separately because this start previous is equal to null here will not be valid here because here the start becomes null. Now let's see how we can delete a node that is in between the list. Suppose we have to delete this node and we have a reference that refers to this node. Now for deletion of this node, the next part of this node should refer to this node. And this node is referred by p previous. So next of p previous should refer to p next. So we write p previous next is equal to p next. Now the previous part of this node should refer to this node. This node is referred by p next. So previous of p next should refer to p previous. So we write p next previous is equal to p previous. And so now this node is removed from the list. So this is how we can delete a node from the between of the list. Now let's see how we can delete the last node of the list. We need a reference to this last node. Now after deletion of this node will become the last node. So its next part should be null. And this node is referred by p previous. So we write p previous next is equal to null. And now this node is removed from the list. Now this was the case of deletion in between the list. We can see that this is statement p next previous is equal to p previous will not be valid here because here p next is null. So these two cases have to be handled separately. This method will delete the first node of the list. If the list is empty, we'll just return. If the list has only one node, then we'll delete it by writing start equal to null and return. Otherwise, we'll delete the first node by writing these two statements. Now this method will delete the last node of the list. If the list is empty, we'll just return. If the list has only one node, we'll write start equal to null and return. Now if the list has more than one node, then we'll find reference to the last node of the list. So after this loop terminates, p will refer to the last node of the list and we'll delete that node by writing this statement p previous next equal to null. This method delete node will delete a node that contains this value x. If the list is empty, we'll just return. If the list has only one node and that node contains value x, then we'll delete it by writing start equal to null. Otherwise, we'll display this message that x is not present in the list. Now, if the list has more than one node and if x is present in the first node, we'll delete it by writing these two statements and return. Now, if x is not present in the first node, then we'll come here and we'll find reference to the node that contains value x. So this loop will stop when either p next becomes null or when this break is executed. Now after this loop terminates, if p next is not equal to null, it means that x is present in a node that is in between the list. So we delete that node by writing these two statements. Otherwise, p next will be null, that is p will refer to the last node. And if x is present in the last node, then we'll delete it by writing this statement. Otherwise, we'll print this message that x is not present in the list. In main, we have called these methods in cases 7, 8 and 9. Here we have called this method delete first node. Here we have called this method delete last node. And here we have called this method delete node. Now let's run this program. This is our initial list. Now we'll delete the first node. So the first node has been deleted. Now we'll delete the last node. The last node has been deleted. Now we'll delete node 3. So node 3 has been deleted. Now we'll delete node 4. So node 4 has been deleted. In this video, we'll see how to reverse a doubly linked list. Suppose this is the list that has to be reversed. After reversal, it will look like this. First node will become the last node, so its next part will be null. Last node will become the first node, so its previous part will be null, and start will refer to this node. And the previous and next references of all other nodes will be changed accordingly. This is the code that will reverse our list. We'll take two references, P1 and P2. Initially, P1 will refer to the first node and P2 will refer to the second node. Now P1 next equal to null, so this will become null. P1 previous is equal to P2, so this will refer here. Now P2 is not equal to null, so this loop will execute. Now P2 previous is equal to P2 next, so this previous part will refer here. P2 next equal to P1, so this is P2 next, it will refer to P1. P1 equal to P2, so P1 will come here, and P2 equal to P2 previous. P2 previous refers to this node, so P2 will come here. Now P2 is not equal to null, so again this loop will execute. P2 previous is equal to P2 next. This is P2 previous, it will refer to P2 next, so this will refer here. P2 next is equal to P1, this is P2 next, so it will refer to this node. P1 equal to P2, and we have P2 equal to P2 previous, so P2 comes here. Now again P2 is not equal to null, so this loop will execute. P2 previous is equal to P2 next. This is P2 previous and P2 next is null, so P2 previous will become null. P2 next is equal to P1, so this will refer here. P1 equal to P2, so P1 will come here, and P2 is equal to P2 previous. P2 previous is null, so P2 will become null. Now P2 is null, so this loop will terminate, and next we'll assign P1 to start, so start will refer to this node. So now we can see that our list has become reversed. This is the method reverse list that will reverse a double linked list. If the list is empty, we'll just return, because in that case P1 will be null and accessing P1 next will give us error. In our method main, we have called this method in case 10. We've called this method reverse list here. Now let's run this program. So this is our initial list. Now the list has been reversed. In this video, we'll learn about circular linked list. In a circular linked list, there is no null link. The link of last node refers to the first node. Each node has a successor and all the nodes form a circle. Now for maintaining a circular linked list, we generally take a reference referring to the last node of the list. So last link refers to first node of the list. If we take a reference referring to first node of the list, then for both insertion and deletion in the beginning and at the end, we'll have to traverse the whole list. For example, if we have to insert a new node here in the beginning of the list, then link of this last node should refer to that new node. And for that, we'll have to traverse the whole list because we'll need a reference to this last node. So it is better to maintain a reference referring to the last node of the list. In this case, insertion in beginning and at the end and deletion in the beginning can be done in constant time. There's no need to traverse the whole list. Now, one of the uses of circular linked list is an implementation of queue, because by using this list, we can perform insertion and deletion in a queue in constant time. Now, let's see how we can implement a circular linked list. We've implemented a single linked list as circular list, so there is only one link part in the node class. This is the circular linked list class. This reference last will always refer to the last node of the list. In this constructor, we have initialized it to null. Now this is the display list method that will display our list. If the list is empty, we'll just return. Otherwise, we'll take a reference P and make it refer to the first node of the list. Inside this do while loop, we are printing the info value of each node and we are moving this reference P forward. Now P is stopped when it refers to the first node. In non-circular list, we stopped P when P became null because their null was present in link of last node. Here link of last node refers to first node. So we have to stop when P refers to the first node or when P is equal to last link. This is why we have used a do while loop here, because initially P is equal to last link and we have to stop when P becomes equal to last link. So if we use a while loop, then it will never be executed. So this was the display list method. We will see how to make all other methods in the coming lectures. This is the method main where we have tested the circular linked list class. Here we are creating a new object and in this while loop we are performing different operations. In this video, we'll see how to insert a new node in a circular linked list. First, we'll see how to perform insertion in the beginning of the list. We allocate a new node. Now this node will become the first node. So link of this last node should refer to this node. But before doing that, first we'll make link of this node refer to this node. So we'll write temp link is equal to last link. Now we can change last link and make it refer to this new node. So now we write last link is equal to temp. So this is how we can insert a new node in the beginning of the list. Now let's see how we can insert in an empty list. For an empty list, last is null. We allocate a new node. Now this is the last node of the list. So last should refer to this node. We write last equal to temp. Now last node should refer to the first node. And this is the only node of the list. So this is the last node as well as the first node. So link of this node will refer to itself. So we write last link is equal to last. So this is how we can insert a new node in an empty list. Now let's see how we can insert a new node at the end of the list. We allocate a new node here. Now this node will be the last node of the list. So link of this node should refer to this first node. So we write temp link is equal to last link. Now link of this node should refer to this node. So we write last link is equal to temp. Now this node is the last node of the list. So last should refer to this node. So we update last and make it refer to this new node. So this is how we can insert a new node at the end of the list. Now insertion in between the list is same as in non-circular linked list. This method insert in beginning inserts a new node in the beginning of the list. This method insert in empty list inserts a new node in an empty list. This method insert at end inserts a new node at the end of the list. This method create list we have made with the help of these two methods, insert in empty list and insert at end. For inserting the first node, we have called this method, and for inserting rest of the nodes, we have called this method. Now this method insert after will insert a new node after the node that contains value x. Here first we are finding reference to the node that contains value x. We have already seen why we need to use a do while loop here. Now in non-circular list, here we had p equal to null. In circular list, here we have this p equal to last link. And we have put this additional condition here, p info is not equal to x. So if p is equal to last link and p info is not equal to x, then we print this message that x is not present in the list. Otherwise, we insert the new node after the node referred to by p. If we have to insert the new node after the last node, then we have to update the value of last. This is the method main where we have called all these methods. In case 2, we have called this method. In case 3, we have called this method. In case 4, we have called insert at end. In case 5, we have called this insert after. Now let's run this program. This is our initial list. First, we'll insert a new node in the beginning of the list. So this 11 is inserted in the beginning of the list. Now we'll insert a new node at the end of the list. So this 22 is inserted at the end of the list. Now we'll insert a new node after node 3. So this 33 is inserted after node 3. In this video, we'll see how to delete a node from a circular linked list. First, we'll see how to delete the first node of the list. Now, after deletion of this node will become the first node of the list. So, last link should refer to this node. So, we'll write last link is equal to last link link. And so, this node will be removed from the list. Now, let's see how we can delete the only node of the list. For deleting the only node of the list, we just have to write last is equal to null. And this node will be removed from the list. Now, let's see how we can delete the last node of the list. For this, we need reference to predecessor of the last node. Now this will become the last node, so its link should refer to this first node. So we write plink is equal to last link. Now this becomes the last node, so last should refer to this node. So we update last and make it refer to this node. So now this node is removed from the list. This is how we can delete a node at the end of the list. Now let's see how we can delete a node in between the list. Suppose we want to delete this node. For that, we need a reference to the predecessor node. Now for deletion of this node, link of this node should refer to this node. So we write plink is equal to plink link. And so this node is removed from the list. This is the same as in non-circular single linked list. Now let's see the code for all the cases of deletion. This method will delete the first node of the list. If the list is empty, we'll just return. If the list has only one node, then it will be deleted by writing last equal to null and will return. Otherwise, we'll delete the first node of the list by writing this statement. Last link is equal to last link link. This method will delete the last node of the list. If the list is empty, we'll just return. If the list has only one node, then it will be deleted by writing last equal to null. Otherwise, we'll find reference to second last node of the list. So after this while loop terminates, P will refer to second last node of the list, and we can delete the last node by writing these two statements. Now this method will delete the node that contains value x. If the list is empty, we'll just return. If the list has only one node and that node contains value x, then it will be deleted by writing last equal to null and we'll return. If the list has more than one node and x is present in the first node, then that first node will be deleted by writing last link is equal to last link link and we'll return. Now if x is not present in the first node, then we'll find reference to predecessor of the node that contains value x. And after that, we'll delete that node from the list. If the last node is deleted, then this reference last will be updated. Now in main, we have called these methods in cases 6, 7 and 8. Now let's run this program. First we'll delete the first node of the list. So the first node is deleted. Next we delete the last node. The last node is deleted. Now we'll delete node 4. Node 4 is deleted. Now we try to delete a node that is not present in the list. So it displays this message. In this video, we'll see how we can add a linked list at the end of other linked list. Suppose we have these two single linked lists and we want to add this list at the end of this list. So we have to traverse this list and find a reference to the last node of this list. This is how we can find this reference. Now we have to make link of this node refer to first node of this list. So we write plink is equal to start 1. So now this list has been added at the end of this list. Now let's see the code for this. This method concatenate will add this list is sent as argument to the list object that calls this method. If the first list is empty, we'll make start equal to list start and return. If the second list is empty, we just return. Otherwise, we'll find reference to the last node of the first list. So after this loop terminates, P will refer to the last node of the first list. And after that, we'll make plink equal to list start. Now here in main, we are testing this method, concatenate. Now let's run this program. So this is the first list and this is the second list. After concatenation, the first list is this. Now we'll see how we can perform concatenation in circular linked lists. We have these two circular linked lists and we want to add this list at the end of this list. Now in non-circular list, we had to traverse the first list to get a reference to the last node. But here we don't have to traverse because we already have a reference to the last node of the list. Now to add this list at the end of this list, we have to make link of this node refer to this node. But if we change link of this node, we'll lose the link to this node. So first we make a reference P refer to this node. So first we write P equal to last link. Now we can change link of this node. So we write last link is equal to last one link. Now link of this node should refer to this node. So we write last one link is equal to P. Now we make last refer to this node. So we write last equal to last one. So this is how concatenation is performed in single circular linked lists. Now let's see the code for this. This method concatenate will add this list sentence argument to the list object. It calls this method. If the first list is empty, then we'll make last of first list refer to last node of the second list. If the second list is empty, we'll just return. Otherwise, we'll add this list at the end of the first list by writing these statements. Here we are testing this method. Now let's run this program. This is the first list. This is the second list. After concatenation, this is the first list. In this video, we'll see how to use a header node in a linked list. A header node is a spatial node that is present in the beginning of the list. The link part of this node refers to first real node of the list. So these are the real nodes of this list and this is the header node. Info part of this node can be empty or we can use it to store some useful information about the list like number of nodes in the list. We maintain a reference head that always refers to this header node. So head link refers to first node of the list. This header node is never deleted. It exists even if the list is empty. For an empty list, the link part of this header node is null. Now use of header node simplifies some operations because by using a header node, we ensure that each node has a previous node and there is a node even if the list is empty. By using this header node in the list, we can reduce some special cases in our code. For example, in the methods delete node and insert before that we had written in single linked list class, we can remove first two special cases if we use a header node. We'll see this in our program. This is the class node and this is the class header linked list. We have taken a reference head that will always refer to the header node of the list. In this constructor, we are allocating this header node and we are making this reference head refer to this header node. This method display list will display the list. If head link is equal to null, it means that the list is empty and we'll just return. Otherwise, we'll traverse the whole list and print the contents of the list. This is the method insert at end. Let's see this method insert at end for a list without a header node. This is the method insert at end for a single linked list without a header node. So here we have this special condition and this special condition is not required if the list has a header node. This is the method insert before that will insert a new node before a node that contains value x. Let's see this method for a list without a header node. In this case, we have these two special conditions before we find reference to predecessor of node containing x. If the list has a header node, then those two conditions are not required. This is the method insert at position that will insert a new node at position k in the list. Let's see this method for a list without a header node. If the node has to be inserted at position 1, then we have to put the special condition. While if the list has a header node, then that condition is not required. This is the method delete node. Let's see this method for the list without a header node. Here we have these two special conditions, and these special conditions are not required if the list has a header node. This is the method main, where we have tested all the methods of header linked list class. Here we have called this method insert at end, insert before, insert at position, delete node, and reverse. Now let's run this program. This is our initial list. Now we'll insert a new node at the end of the list. This new node is inserted at the end of the list. Now we'll insert a new node before a given node. So this 55 is inserted before node 5. Now we'll insert a node at a given position. So this 44 is inserted at position 4. Reverse the list. In this video, we'll learn about sorted linked list. Some applications require data to be stored in sorted order. If we have our data in linked list, we can maintain the list in sorted order by inserting nodes at proper place in the list. Now let's see how we can create a sorted linked list. Initially the list is empty. We have to insert new node with value 20. It will be inserted as the first node. Now we have to insert 10. 10 is less than 20, so it should be inserted before 20. So it is inserted in the beginning of the list. Now we have to insert 30. It is more than 20, so it will be inserted at the end. Now we have to insert 15. It will be inserted between these two nodes. Now we have to insert 35. It will be inserted at the end. 5 will be inserted in the beginning of the list. So we can see that if the new element to be inserted is less than the element in the first node, it is inserted in the beginning of the list. And if the new element to be inserted is greater than the element in the last node, it is inserted at the end of the list. Otherwise, it is inserted somewhere in between the list. Now we have taken a single linked list. So we already know how to insert a new element in the beginning, at the end, or in between the list. Now searching in a sorted linked list takes less time because we can stop as soon as we get an element that is greater than the element to be searched. For example, in this list, if we have to search element 12, then we start at this node, we go to this node, and when we reach this node, we can say that 12 is not present in the list. Now let's see the program for sorted linked list. This is a sorted linked list class. We have only one method for inserting a new node in the list. We don't need methods like insert in beginning or insert at end because they'll disturb the sorted order of the list. Inside this method only, the position of the new node will be decided depending on its info value. Here we allocate a new node. Now if the list is empty or new element to be inserted is less than start info, then we have to insert the new node in the beginning of the list. So here we are inserting the new node in the beginning of the list by writing these two statements, temp link is equal to start and start equal to temp. Otherwise we find reference to the node after which the new node has to be inserted. So here in this loop we are finding that reference, and after that we are inserting that new node. We have already seen in single linked list how these two statements insert a new node in between the list or at the end of the list. Now this loop will terminate when either this condition becomes false or this condition becomes false. This condition will become false when p-link becomes null. That is when p refers to last node. And so in that case, new node is inserted after the last node. This condition will become false when p-link info is greater than data. In that case, p refers to predecessor of the node that has info value greater than data. So in this case, new node will be inserted after the node referred to by p. This is the create list method. We have inserted all the nodes. With the help of this method, insert in order. This is the method search. If the list is empty, we'll just return. Now the search terminates in 3 cases. First, when the search is successful and the value x is found in the list. Second, when we reach a node whose info value is greater than the element to be searched. And third, when we reach the end of the list and p becomes null. So after this loop terminates, if p is null or p info is not equal to x, it means that element x is not present in the list. Otherwise, it is found in the list at this position. Now in this method main, we have tested the sorted linked list class. Now let's run this program. This is our initial list. Now we insert a new node. This 5 is inserted here. Again we insert a new node. This 1 is inserted in the beginning of the list. Again we insert a new node. This 10 is inserted at the end of the list. Now we search for a node. 9 is present at position 7. Now we search for a node that is not present in the list. 67 is not found in the list.